Okay, so the first theorem you guys come across, theorem 5.1, says if you have a set V1, V2 up to Vk, if this is an orthogonal set of non-zero vectors in Rn, then these vectors are linearly independent. Okay? I thought it might be a good exercise to have you set up the proof. So, let me pause for a couple minutes and see what you guys do with that. I mean, again, it's unpacking, right? It's taking this word, linearly independent, right? And you want to say what that means. So I'm going to write an equation down, right? What's the equation that goes with that? C1V1 plus
C2V2.
Yeah.
Plus plus CKVK.
Equals this zero vector, right? I mean, these are all vectors. I'm not going to put all the arrows, but we know that that's the equation, right? And so the very end of the proof, maybe I'll go all the way down the screen here. The very end of the proof, what I hope I show is that C1 equals 0, C2 equals 0, and CK equals 0, because if I get all that, so that'll prove that the vectors are linearly independent, right? I mean, there's the end of the proof. I need to have this equation somehow give me the fact that we know that that's one solution, right? But we want to show that that's the only solution. Okay. So, what you do, and this is kind of cool, we need to use the fact that the set is orthogonal, right? It's an orthogonal set. And that has everything to do with dot products, right? So what I'm going to do is I'm going to take, so if we have this, then what we can do is we can take this side and dot it with V1. Okay? And we'll also dot the other side with V1. But of course, if you dot the other side with V1, what do you get? What's the dot product of 0 and V1? It's 0, right? It's 0. So now, let's look at the left-hand side and see what I learned from that. Because this is C1V1 plus C2V2 plus dot 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 plus CKVK, right? What do you think I should do next on the left? Can you distribute with a dot product? Well, yeah, you can. You can distribute actually with matrix multiplication too, but with dot products, yeah, that's a property. You can say that this is C1V1 dot V1 plus C2V2 dot V1 plus, well, I'll put dot 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 here, and then I'll say CKVK dot V1. All that equals the number 0, because dot products spit out a number. right? Now, the fact that the set is orthogonal tells me something. It tells me, what do I know about v2.v1? That's 0. Because any two, right? Matter of fact, they're all 0, except the only thing I don't get from this is I don't know about v1.v. Well, actually, I do know. v1.v1, this is non-zero, right? Because the only way v1.v1 can be 0 is if what's true? If what? If it's the 0 vector. But we said that this is an orthogonal set of non-zero vectors, right? There's only one vector you could dot with itself and get 0, and that's the 0 vector. So it's interesting what just happened. Because if you look at what we have now, we have C1 times something non-zero equals 0, right? And what does that prove? C1 is 0, right? Well, guess what? I'm partway there. So what do you do next? Next, C1v1 plus C2v2 plus ... plus CKvk equals, and what you'll do is you'll dot it with v2, right? And what's going to happen? The same logic proves that C2 equals 0, etc., right? So you'd have to do k different dot products, right? All the way up to the last one, you'd dot it with vk, and that would prove that ck is 0. But I think that's a pretty slick proof. So I wanted to make sure I showed you that. Fact. It is nice to have an orthogonal basis. Now that's an opinion, right? Nice. But we're going to see it's a fact. There are a lot of nice properties you get from the fact that it's orthogonal, which is why when you take I, J, and K, that's orthogonal, right? So the next few theorems kind of go into some of this, and actually the next few sections go into this. This is kind of like one of the themes from the beginning of the chapter. But what Noah was talking about, that comes into the second half of this section when we start talking about orthogonal matrices. Anyways, let's give you a theorem. Here we go. Theorem 5.2. So, suppose v1 to vk, these vectors, let this set be an orthogonal basis for, well, I guess it'd be for Rk, because there are k vectors, right? So suppose you have this orthogonal basis. Actually, let's do better. Let's do better. Come on, Paul. Let it be an orthogonal basis for a subspace W of Rn. Okay? So we're working in Rn. Maybe we only have 3 of the vectors or something like that if we're in R4. And let W be a vector in W. So wait a minute. Little w, where does it live? It's a vector in the subspace, right? Little w is going to be a vector in the subspace. Okay. If that's true, then there exist unique constants C1 up to CK such that, so I'm going to write the equation and you tell me what it says. What does that say, that equation I just wrote down? It says that W can be written as a linear combination of the vectors. Actually, I guess we get that for free just because it's a basis, right? But there's more. These constants are given by a formula. So here's the formula that's important. Let me write it down. Ci, so that could be C1 or C2 or CK, is equal to a dot product over a dot product. So it's equal to W dot VI. What's that?
C1 or CIE?
CI. I'm using I. So it'll work for C1, but it'll also work for C2 and everything up to CK. So it'll be W dot VI over VI dot VI. Okay? So that's what we have. So as far as the proof goes, again, the first part, that's just because it's a basis, right? It's the second part that might take a little tiny bit of work here. And it's also the second part that's really useful. As a matter of fact, this is what section 2 is all about. Okay? So what you're going to read for next Monday is all about this whole idea. Finding these constants. But anyways, let's do a little proof. So notice that W dot VI, what does that look like? Well, we have an expression for W because we wrote it as a linear combination. So let's rewrite it like this. So you guys understand what I want to put in the parentheses, right? C1 V1 plus dot 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 plus CK VK. Okay? And I guess my question is, what am I going to do next? There's the same trick we did in the last theorem. Distribute. And when we distribute, what happens? Everything becomes zero, except, right? You get a whole bunch of zeros, except for whatever I is, right? So you're going to get CI VI dot VI. Right? You guys see how that works? Now again, what I was trying to do is come up with this red formula. We almost have it now. What's the only thing you have to do to get the red formula? Here's my equation. W dot VI is equal to CI times the dot product VI dot VI. Yeah. Now, can I divide by that? You always have to check that you're not dividing by 0. But I know that because the only way VI dot VI could be 0 is if VI were 0, right? And this is a basis. A basis can't have 0 in it, or it would be linearly dependent. So now just divide both sides by VI dot VI, and you're there. Okay?
I'm gonna put that one real quick.
Sure. Yeah, so I want to try and talk a little bit about example 5.4 from the book because it's useful. So we have W is 1, 2, 3. And it says, find the coordinates with respect to the orthogonal basis. What you're really doing is you're trying to express it in terms of V1, V2, V3. Right? We'll go back to those examples. So they say V1 is 2, 1, negative 1. V2 is 0, 1, 1. And V3 is 1, negative 1, 1. Okay, now guys, look, on the paper that I wrote. If I told you guys, I want you to write W as C1 V1 plus C2 V2 plus C3 V3. Could you do it? Could you do it before you ever got to this chapter? How? Stephen was nodding. What were you thinking?
Or you could just make a matrix.
Yeah, we've done this before, right? You put a matrix. You put the columns V1, V2, and V3 here. And then you do this. And then you put W here. And what do you do to the matrix? What we always do, right? And then you get the solution. And the solution will give me C1, C2, and C3. That was like the theme of the first half of the whole course.
That's like an augmented matrix.
Yeah, this is the old way of doing it, okay? Now I have a better way. So this is the old way. That's the old way. The better way is this. The better way is this. Since V1, V2, and V3 is an orthogonal basis, actually, do we know that? Is that true? I hope so. If I dot V2 and V3, I get 0. Yeah, it is. It's from the book, from the example. We have a formula. CI equals W dot VI over VI dot VI. Okay? This is faster than going through all the row operations. And check this out. You guys, let's get the first one. What is C1? Well, what's W dot V1? Well, we could do that, right? 2 plus 2 is 4, minus 3 is 1. And what's V1 dot V1? Well, it's dotted with itself. 2 times 2 is 4, plus 1, plus 1, right? 1/6. So that's C1. That didn't take very long. And you can get C2 and C3 in the same amount of time. And so they do it here. 1/6, 5/2, and 2/3. Done. So again, my theme, that orthogonal basis is nice, this is one of the reasons. Okay? All right, let's take our break, guys, and we'll come back in 10 minutes and go from there. Okay? That's the fact. It is nice to have an orthogonal basis. I'm trying to sell that to you. Trying to make you remember it. Okay? And I'm going to say this, maybe to emphasize the point. It is really nice to have an orthonormal basis.
Orthonormal?
Yeah, the word, do you,
That's how it's pronounced.
yeah, orthonormal. Do you guys know what that means?
I honestly just thought that was orthogonal basis when I first read it. Like I just read it too quickly.
Yeah, I could believe it. But it has this other word here, normal.
Doesn't it mean it's a unit?
It means they are unit vectors. That's right. So an orthonormal means an orthonormal basis is an orthogonal basis where each vector is a unit vector. And why is that so special? Well, you guys have used unit vectors a lot. I mean, when you studied trigonometry, didn't you guys spend like your entire life on the unit circle? Right? So we're used to unit vectors. And how do you make a vector into a unit vector? Well, you take it and you multiply it by its, well, you divide by its length, right? So you multiply by the reciprocal of its length. And so it might not surprise you to, when you look at this formula here, see, if V1 was a unit vector, what would the denominator be? Well, 1. And so you don't even have fractions anymore. I mean, this is really nice when you have an orthonormal basis. And that's kind of the point that the book makes. Next, Theorem 5.3, I don't want to write down. I will just show it to you. And you'll say, aha, I get it. I think. We'll see. Look what they said. Let the Q's be an orthonormal basis. Okay, so notation-wise, we're going to put V for vectors, but we're going to put little q if it's orthonormal basis, right? This is saying, hey, the dot product of any, oh, cool, I can color it? Wow, that's cool. If the dot product of any of these is 1 if you dot it with itself, and it's 0 if you dot it with each other. Okay? Now, the next part, orthogonal matrices. No, let's not color that one. This is kind of part 2. This is what Noah was getting at when I said, hey, what does it tell you if you have an orthogonal set of vectors? He said, maybe you have an orthogonal matrix, okay? First thing you should know is the definition. So let me write this down. Definition. An orthogonal matrix is an n by n matrix. So first of all, it has to be square. Okay? It's an n by n matrix whose, is that fair? Are you guys okay with me using that pronoun for a matrix? I always do. Whose columns form an orthonormal set. Okay? That's really important. They have to form an orthonormal set. That was the point of the quiz question. Okay, so I asked you guys, is this set orthonormal, right? So you had already checked, like, if this is V1 and this is V2. I remember we checked that V1 dot V2 was 0. But for this to be an orthonormal set, what do we need to be true? We need V1 dot V1 to equal 1, right? And does it? Well, I guess if you dot it, you get a fourth plus a fourth plus a fourth plus a fourth, right? So you get 1. So this will work, okay? If you were to take these numbers and put them into a matrix, that would be our first example of what's called an orthogonal matrix. It's a bad name. They probably should have said an orthonormal matrix, okay? But they didn't. If you see orthogonal matrix, by definition, that means the columns are orthonormal. You guys with me? So maybe I'll put that into a matrix for ourselves. Here we go. Q is going to be the matrix. 0.5, negative 0.5, negative 0.5, negative 0.5, and then 0.5, negative 0.5, 0.5, 0.5. Oh, wait a minute. I'm doing the columns. That's all right. It'll work. I'll just transpose it. 0.5, 0.5, negative 0.5, 0.5. And then 0.5, 0.5, 0.5, negative 0.5. And then I'll transpose it with the little apostrophe. Is that our matrix we had? From the quiz? Yeah, that is, right? So this is our example of an orthogonal matrix, right? Q. I wonder if I could, if I do this, will it show it to me that way? Oh, good. So I can show it to you. Okay? So now maybe we can tackle some of the theorems about orthogonal matrices. Oh, so theorem 5.4 is interesting. Let's write it down and think about it and go from there. So let's see. Theorem 5.4. The columns of an M by N matrix Q form an orthonormal set if I write this, is that okay for you? If and only if. And then the if and only if would be this. Q transpose Q is an identity matrix. So let's try that on the MATLAB. So let's see, MATLAB, we have this matrix Q. And so if I take Q transpose times Q, ha! I get the identity. Okay? Now, why is that true? I'll give you a couple different proofs here. Okay? Here's one proof. All right? You see this matrix? What size is this matrix going to be? N by N, right? Because you have Q is M by N, and this is N by M, right? So let,
Q's n by n?
yeah, let A equals Aij be the N by N matrix Q transpose Q. And then what you might ask is, where does Aij come from? Okay? I claim that Aij is equal to Qi dot Qj. Why is that? Well, let me show you. Give me a number for I and for j. Let's take 3 and 4. I is 3 and j is 4. Okay? So watch. We'll go to MATLAB. And I'm going to say, let me look at Q again. Okay. And let's say that Q3 equals Q, I'll put a colon, which gives me every row, and column 3. Do you see how it just picked out column 3? Right? And I'm also going to define Q4 to be the fourth column of matrix Q, right? Now, what would happen if you dot product these two together? You get 0. But notice also, if you do this, Q3 transpose times Q4. Now Q4 is 4 by 1. So if I do Q3 transpose, that's 1 by 4. You get a number, a 1 by 1 matrix, which is 0. You see that? So basically, there are two things that can happen when you transpose and you think of all the different entries. The way this works is Qi dot Qj will equal either 0 if I does not equal j, or what? It could equal 1, right? If what happens?
Q, that is?
Yeah. Qi dot Qj could equal 1 if I equals j. And this describes the identity matrix. IM. So we just proved that this A is actually the identity matrix.
1 if what?
If I and j are the same. So for example, if we go back to MATLAB, and if I do Q3 dot Q3, I get 1. So that's why you get the identity matrix. Okay? And once you have that theorem, you get the next one for free. So I'm not going to prove it in class. I'm just going to show it. Where's theorem 5.5? Here it is. A square matrix is orthogonal if and only if Q inverse is equal to Q transpose. And that's what they say is the most important fact about orthogonal matrices. Because it's pretty hard to find an inverse. Do you remember how we did it?
Put it in some other matrix.
Yeah. And then you had to do all the row operations, right? Wow. It's nice to find the inverse here. What's the inverse this time? Swap the rows and columns. Done. So again, we really like orthogonal, or in particular, orthonormal sets of vectors. And that motivates what we're going to do in the next week, because next class we're doing some research stuff. But all next week we're going to talk about what's called Gram-Schmidt orthogonalization. And this, you take a set of vectors and you generate an orthonormal basis from it. So that's coming. Okay. Let Q be an n by n matrix. The following statements are equivalent. Aren't you glad they only have 3 of them this time? Right? Mm-hmm. So Q is orthogonal. Now look at these next 2. This one says the length of QX is equal to the length of X. Actually, it doesn't quite say length. It says, do you guys know that symbol? That's norm of a vector, okay? And this isn't really talked about till chapter 7, but sometimes you measure distance in other ways. But for us, it's Euclidean norm. And then down here, part C says qx dot qy equals x dot y. Okay? So I guess the take-home message is the following. And let me write it down for you, because I don't think it's spelled out enough in the book. So theorem 5.6 really says that orthogonal matrices and by the way, remember that every matrix is the same as a linear transformation, right? From where to where? Right. In general, it's from Rn to Rm. But if we say an orthogonal matrix, this is automatically n by n. So it's from Rn to itself, right? So orthogonal matrices are actually orthogonal linear transformations from Rn to itself. What's special about orthogonal linear transformations is this. They preserve distances and they preserve, well, it's interesting. The theorem says they preserve dot products, but because of that, they preserve angles. And you guys that are interested in linear algebra for engineering reasons or for video reasons, you want to study. Remember, I showed you Yoda, right? And if you think about linear transformations, there's lots of linear transformations. But if we want to make sure that we're not going to skew our picture, we're not going to change the lengths of anything or the angles, you need your matrix to be an orthogonal matrix. Okay? Because these are equivalent. These are if and only if. All right? So I think that's an important fact. Yeah, it's called an isometry in geometry. An isometry. That's an important idea in mathematics. Okay? This one's a nice one. Theorem 5.7. If Q is an orthogonal matrix, then its rows form an orthonormal set. So hang on a second. What's the definition of an orthogonal matrix?
That they're linear,
No.
independent.
What's the difference between this and the definition? Hold on a second. Where was that definition I posted for you guys? Back here. Ah. There's only one word different. Take a look, guys. All right? The definition is columns. This little theorem says
Columns and rows.
it's rows. Yeah. How do you turn columns into rows? Transpose. All right? I'm going to give you a minute or two and see if you can come up with a proof. See what happens. So I guess, a couple different approaches you could try. At the end, we want, let's see, we want the rows to form the rows of Q
To form an orthogonal set
to form an orthonormal set.
or orthonormal.
Now I claim that that's the same as the columns of what? The rows of Q are the same as the columns of Q transpose. So if I could show that the columns of Q transpose form an orthonormal set, then I'd have it. Basically, you want to show that Q transpose is an orthogonal matrix, right?
You have to work with the inverse.
What's that?
You have to work with the inverse since you know that the inverse.
So yeah, the inverse is involved, right? Didn't we have a theorem? What was the theorem? I forget which number it was, but Q transpose is the same as what? So we know that Q transpose is equal to Q inverse, right? So I guess what we need is to show that the columns of Q inverse form an orthonormal set, and that would do it, right? So the given is that Q is an orthogonal matrix. If we could show that Q inverse is an orthogonal matrix, then I have it, right? So what you can do kind of is this, and the book does this. You could say, okay, let me take the inverse of Q transpose and see what that looks like.
That looks like a 2 there.
A 2?
Right there.
This right here?
No, on the left. Right.
Oh, my Q looks like a 2? This guy. Yeah, I guess I didn't quite close it. That's a Q. Now, what's Q inverse inverse? Q. So far I have Q is the inverse of Q transpose. I guess that's what I have, right? Can I show that the columns of Q inverse form an orthonormal set, or the columns of Q transpose form an orthonormal set? Well, isn't it also true that Q is the same as Q transpose transpose?
Mm-hmm.
So now take a look at these 4 equations, and what you want to do is you want to say, okay, start here and end up here. Q transpose inverse is the same as Q transpose transpose. I guess that shows this. The columns of Q transpose form an orthonormal set. It shows that Q transpose is orthogonal. If the transpose is the same as the inverse, that's how you identify an orthogonal matrix. Does this help? I guess we basically just proved part A. We proved that Q inverse is orthogonal because we just proved that Q transpose is orthogonal. Part B, this is kind of cool. The determinant. So far, we only had one thing we knew about the determinant, I think. We knew that determinant 0 means what? Not invertible, no inverse. Now you have another meaning of determinant. Determinant, if it's plus or minus 1, that's an orthogonal matrix. Okay, so that's kind of cool. Notice the next statement. If lambda is an eigenvalue, how do you read that second part? Yeah, the absolute value of lambda is 1. So where are all the eigenvalues for an orthogonal matrix? They're all on the unit circle. Now you have to understand what I mean by that. Because again, where do eigenvalues live? Let me say something about that, okay? So, where do we find eigenvalues? And the answer is this. What's that stand for? Bless you. Do you guys know what this stands for? No? Oh, I'm sorry.
I don't even know.
This is the complex plane. Do you guys know what this stands for? Yeah, all real numbers. This is called the real number line. Okay. So, you know, I drew this for you guys last time when we were studying Gershgorin disks. If you want to plot the eigenvalues, they're going to be of the form, right? Complex plane numbers are of the form a plus bi. So you go over a and you go up b, right? When we say that for an orthogonal matrix, the absolute value of lambda equals 1 for every eigenvalue, lambda, that means they live on the unit circle, right? So the eigenvalues might be things like 1, or they might be things like I, or they might be things like, how about this would be radical 3 over 2 plus 1/2 I. Okay? Those are all eigenvalues that live on the unit circle in the complex plane. Okay? This is the world where you need to live if you want to study eigenvalues of a matrix. Complex plane. Hey, what happens, remember last time we studied something called the power method, a to the n? And we said that a to the n x is going to approach the dominant, what was it? Yeah, the dominant eigenvector, and then we also talked about the dominant eigenvalue. And the dominant eigenvalue was the one with largest absolute value, right? So in general, what happens is this. If you take a number smaller than 1, closer to 0, and if you multiply it by itself over and over again, what happens? I don't know, like, yeah, like,
3 halves plus 1/2 in I.
yeah, that's also on the unit circle, yeah. But right now I'm thinking about this, guys. The limit as n goes to infinity of 1/2 to the n power, that's 0, right? Anything inside this circle, if you repeat it over and over again, it goes to 0. What about if it's outside the circle and you repeat it over and over again? Like, what's the limit as n goes to infinity of, say, 1.1 to the n power? Well, that's infinity. So there's something very special about being on this circle, that you can repeat over and over again whatever this transformation is, this Q, and it's not going to blow up and it's not going to shrink. Okay? So that's kind of an idea also that I think is worth mentioning. All right.